Question from last time. Okay, the last thing we talked about in our last adventure was this biconditional statement P if and only if Q. That means that if and only if means this implication and this implication, and this is true precisely when we have the same truth values P and Q, right? So P is true. If this statement is true, that means P is if P is true, then Q is true, and if Q is true, then P is right. So let me give you a theorem here where we're going to talk about some equivalent propositional points. Six. Suppose that we have propositions P, Q, and R. Uh, P implies Q, right? Somebody remind me when P implies Q. What are the truth values on that? When is this true?
When P is true and Q is true, and P is false and Q is true, and P is false and Q is false.
That's correct. So this is, in fact, let me go the other direction. When is this false? Only, yes,
When P is true and Q is false.
that is correct. This is equivalent to not P or Q. So, this is false precisely in the case when this is true and this is false, right? And the same is true here. If P is true and Q is false, then both of these are false, right? But every other possibility, there's at least one truth here. So these two are equivalent statements. The implication error of P implies Q is equivalent to not P or Q. Two, P if and only if Q is equivalent to P implies Q and Q implies P. Not P and Q. P and Q not is equivalent to, anybody want to take a stab at this? So this means you can't be both P and Q. All right, so what should that be equivalent to?
Not P, but not Q.
Not P or not P. See if there's kind of a pattern here. Let's see if we can guess this. Not P or Q. Anybody want to guess this? Not P and not Q. Good. Uh. Not. P implies Q. How about this? The key is actually what we've done before, when we talked about this in other. It should be P and not Q. Back to five. Okay. How about this? Uh. Not P and Q is equivalent to P implies not. How about this one? Here's one with a little bit of a different flavor to it. P and Q or. We'll take a stab at this. P and Q or R. This distributes out sort of like multiplication in a certain sense. Now, given that, if you believe in patterns here, P or Q and R. I won't guess at this. This is true, it's like multiplication again. Either Q and P. These are all equivalent propositions, or this list. Now, here's what sets this course apart. Why? All right, let's put a bounty on some of these tests. Well, which ones do you think are the easiest to, so you guys are kind of nodding politely, right? How many of you completely see why this is true immediately? Anybody? Well, maybe I don't either. Well, let's put some bounty on some heads here. Somebody pick one we'd like to see. Which one? 8. 8. Okay, why is 8? So we'll do some selected proofs. How about 8? How do we show the two propositions are equivalent? What do we got to do? We got to look at the dang truth table, and that's it, right? And you made our life difficult because we've got 8 things to do, but that's okay, right? Because this one, number 8, involves 3 propositions, right? So we've got to go through 8 possibilities. So let's just look at the tables here. P, Q, R. These are our players here. And I want to need 8 of these. Now, let's true, false, 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 true, false, true, false, true, false, false. Okay, so I want to compare these two. I've got a column for B. Let's do a column for Q and R. Because that's going to be one of our things here. Okay, Q and R. So I'm comparing these last two columns here. What does it take to be true here? You have to have a double true. Everybody agree with that? Okay, I've got a double true here. Double true here. And that's that. So everything else must be false. Because there's at least one false in all the others, right? Now we have P or Q, P or R. So let's move a couple columns here. Or Q, P or R. Okay. So for these, we're comparing the first two columns here. What does it take to be false here? Double false. Everybody agree with that? So the only way that P or Q is false is if they're both false. All right. Well, double false. Last two. Everything else must be true. Everybody agree with that? What about P or R? Now I'm comparing these two, and it's the same deal in that it's only false if I've got a double false, right? So let's check this out. There's a double false here and a double false in the last one. Everything else must be. Okay, so far. Okay, I think I've got everything I need. So let's first do. Let's first do P or Q and R. Which is what we started with here. So we're comparing this to this. Well, I'm sorry, we're using these two columns and it's an OR, right? So what do I need to be false over here in the orange column? I need a double false. Everybody agree with that? All right, let's check it out. When do I have a double false? Nope, 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 nope. There's one. There's one. Okay, so the last three are double false. So everything else is true. Okay. Okay, and in the last one, we are going to look at what are we going to look at? P or Q and P or R. Right. So now we're comparing, we're looking at these, and it's an and, right? So what do I need to get a true here? I need two truths. Do I agree with that? Okay, let's go down here. Two truths, two truths, two truths, two truths, two truths. True, false, false, true, false, false. And there's your proof. Because the truth tables match all of these. Yes,
See, when it's written out, why do you eight columns, but how can you know you need eight just by looking?
because I've got three letters, 1, 2, 3, right? And for each of those, there's two possibilities. So 2 times 2 is 4, times another 2 is 8, right? And so, and if you think about it, that's kind of the way that we did the binary here. 4, 4, 2, 2, 2, 1, 1, 1. Does that make sense? Okay. How about others? How about 5? Let's look at 5. Let's prove that that's the same too, because that one, I got some eye rolling when we did that one. Has everybody got what they need here? Let's look at 5. Let's go through that one. Okay. Now, 5's a little bit more convenient because I'm only involving 2 propositions, right? So I only need 4 rows, so that's a little bit easier. Let's look at proof 5. Okay, so our players here are PQ. Right? That's cool. So true, true, false, false, true, false, true, false. So let's go through comparisons here. Okay. Just to make my life easier, I'm going to do this before I knot it, before I put the knot in front of it. P implies Q. How should P implies Q read here? Correct. True, false, true, true. Because if you start with false, you get true and everybody okay with that? Okay. So the not, the same thing. So this is mine. There's one of them. I also need P and not Q. So just for ease, let me do not Q here. That's false, true, false, true. And so the P and not Q. What do I have here? Let's check this out. We're P and not Q, so I'm looking at this and this. It's an and. So I need the double true be true. So that should be false. That should be true. That should be false. And that should be. So notice. Therefore. Everybody okay with this? Can somebody think of another way to do this? Somebody think of a way to do this using the other ones without the tape? Yes. So here's another way. Okay. Yes.
So we have first like what theorem 1, the
P implies Q equivalence, but not P or Q. Then, so we're trying to negate 1.5, so we can negate it using 4.
Good, good. So, not P or Q. Everybody okay with that? That's statement number one. Now, the key observation here is, yes, so it must be true that not P implies Q is equivalent to not P and Q or Q, right? All I did is I knotted this and then I put a knot on that. Everybody agree with that? Ooh, look at this mess. Oh, somebody please help rescue me. How can I fix this? Make it better. That's a not Bill or Fred, right? Look at 4. 4 tells you how to not Bill or Fred. Not P, and not Q. This is by 4. To not P or Q, it's not P and not Q. Everybody follow that. Now let's just clean this up again. What's not P? P. So follow the train. This is equivalent to this, which is equivalent to this. So in conclusion, not P implies Q is equivalent to P and that way we use the tools that we have developed. It didn't have to go through that big table. Everybody okay with that? Okay. Any questions on that? Okay. Let me give you a sentence that all of you have dealt with at some point. Right, this takes me back to my high school days in algebra, so first solving quadratics, right? Exploiting this 25. This is technically not a proposition. Somebody tell me why? Right, a proposition is a statement that is what? It's either true or it's false. And this is a big fat question mark. I don't know what to make of this until I specify a value for X, right? So for example, if X takes on the value 5, this becomes a true proposition. If X takes on the value -5, it's true. If X takes on the value 4, this is a false promise. Right? Everybody agree? And so Uh, so. This is a true proposition. If x equals +1 and false otherwise. Such a sentence we're going to refer to as an open sentence. All x squared equals 25 and open sentence. That is, its veracity cannot be determined until we specify the value of x. Different open sentences can have different solution sets. In different universes. Let me tell you what I mean by that. So when I write this equation here, I'm playing a little bit fast and loose, right? What do I really need? What universe does that come from? Right? By universe, I might mean the set of all possible values of x. Now I said here that this is a true proposition of x equals ±5, false otherwise. Can you give me an example of a universe in which it's impossible to make this proposition true? That is the simplest and most succinct way to do it. Any universe where there is no ±5. Let me give you an example. Consider all the real numbers that are irrational. Right? 5 is a rational number. In this universe, there's no solution that makes this work because we can only take values that are irrational, and no irrational number squares to 25. Everybody okay? So the universe can, the place where we choose our x's from can make a big difference. So let me give you kind of a definition to formalize this all. And I'll give you an interesting example of what happened here. Definition. The truth set of an open sentence which we will sometimes denote as P of X. So this is a sentence, an open sentence involving some variable X, like for example, the sentence might be x squared equals 25. Right? What is the truth set? Is the collection of all x in our specified universe that makes P of x true. So for example, if my universe is the integers and my sentence is x squared equals 25, the truth set is +5 and -5. So. Let's look at some examples. One, two. Uh. Okay, so consider, um. Consider P of X to be the open sentence, x squared plus 4, 0. Okay. Now, what the true set of this is depends on the inverse. We're all familiar with complex numbers. Everything in the form. A plus BI, where A and B are real numbers. Has anybody not seen complex numbers? Right, and remember I squared is what?
-1.
-1, right? If my universe is complex numbers, anybody tell me what the true set is?
2i minus 2i.
Good. Because when you square 2i or minus 2i, you get -4, don't you? Right. What if my universe is real numbers? What's the true set now? A lot of you probably seen this notation before. This means the empty set, that is the set that contains nothing. Right? There's no solution to this in the reals, right? Because there's no real number that squares to a negative. Everybody okay with that? So as you can see, the universe we pick greatly affects the true set. Let me give you, so let me give you another definition for this hand in hand with this. Definition. In a specified universe, two open sentences X and QX are equivalent. If their truth sets are the same. So we say two open sentences are equivalent if their true sets are exactly the same. So everything that makes P of X true makes Q of X true and vice versa. I'm okay with that. Anybody give me an example of equivalent? Anybody, give me example of.
2x equals 3 and 3x equals 4.5.
So it might be a problem with that. Show you an example. Let me start out, because I've got a pea-sized brain, let me start off with some. In any. That and that are equivalent. Right, that's the smart aleck answer, but it's worth reporting, right? Anything should be equivalent to itself. And notice P of X has exactly the same proof set as P of X. Okay, well, how about something that's a little bit less silly? Let me give you another example. Also, X plus 2 equals 3 is equivalent to X equals 1. This might seem like a silly example. Because in any versus works. Now, here's the problem, which here's the potential problem. I haven't thought about yours yet, but uh, 3x plus 2 is 20.
X minus X equals 0.
Not necessarily. Yeah. The word universe allows unique division by 3. How did you get from here to here? Subtract. That's kosher. 3x equals 18. But then you divide it out by 3. You might not be able to do this. But can anybody think of an example? Yeah.
Universe, even numbers. Or real numbers.
Yes, but even in the universe of even numbers, X is in that universe. And it makes both of these equations work, right? So if your universe allows you unique division by 3, it'll work, and it might work in some others, but I'll give you a universe where this doesn't work. This is actually, I'll bring this example up because in my recommended textbook, at least in an earlier, they put this in as an example. They said, this and this are equivalent in every universe, and they're not. Let me give you a universe. In a certain sense, right? A clock with only 6 hours. My universe consists of, to emphasize the difference, I'm going to put a little bar over. That's exactly right. As some of you may have seen it, some of you may not. How many of you have ever seen modular arithmetic? Maybe a couple of you. Let me show you how this works. The way you add two things in this animal is just like regular. Right, 1 bar plus 1 bar is 3 bar, 2 bar plus 3 bar is 5. But the question becomes, what happens if you go over? Well, you just cycle around like a clock. If it's 11 o'clock, what time is it 2 hours later? Let's assume we're not in the military. It's 1 o'clock, it's not 13 o'clock, right? Because you go back, 12 goes back to 0. And it's the same principle here. When you go to 6, you're going back to 0. So this is the same thing, 6 bar, 7 bar, 8 bar, 9 bar, 10 bar, 11 bar, 12 bar, it cycles like that. So what's 3 bar plus 4 bar? 1. 7 cycles back to 1. Everybody agree with that? What's 5 bar plus 5 bar? It's 4 bar. Everybody agree with that? Another way to think of this is -1 bar, -1 bar, -2 bar, right? That's kind of a fun way to do it. Multiplication is the same. You just multiply them regular and just subtract off multiples of 6 until you're in that range. So what would 3 bar times 5 bar be?
3 bar.
Maybe, I think it's right. Let's see, what is it, 15 bar? That's not there. So subtract 6, 9 bar, that's not there. Subtract 6, it's 3 bar. So you're right. Everybody okay with that? See how this works? Now, in this universe, x equals 6 translates to this. Everybody agree with that? And that translates to 3x, 3 bar x is equal to 0. Everybody agree with that? So what is the truth said here? On 0 bar. If x equals 0 bar, then x is 0 bar. That's it. Everybody agree with that? How many solutions you got for this? One of them is circle 0. Anybody give me another solution? And another? This one has 3 solutions. So I usually expect these two, x is 6 and 3x plus 2 equals 20, have the same solution set. But here I built a universe, this mod 6 universe, if you will, this 6 clock equation, where this equation has only one solution. This has 3. Okay. So you got to be a little bit careful about the universe that you're living in. Whether something is equivalent or not. So let me kind of finish off this example with one more. Somebody give me an example of a universe in which these two are equivalent. Oh, that's a good universe. These are equivalent in natural numbers. Which I will call n. It's all positive. Can you give me a universe where they're not equivalent? That works. My universe is the integers or real numbers, these are not the same. They're not equivalent. Okay. Any questions so far?
On the last example, how did you get the 2 bar and 4 bar solution. I know 0 plus.
Right, because imagine just for a moment that you plug in 2 bar to this. Right, and that's gonna be 6 bar, which is my 0, right? And the same with 4. Basically speaking, the thing that these have in common is they're even in a certain sense. And when you take that even number and multiply it by that 3, you're gonna have a multiple of 6, which is always gonna be C.
Thank you.
Okay. Um. Simple. Uh. This example, probably, I should put this down below, like the definition here. Um. Uh, so here's a couple of sentences that we may be interested. Consider the sentences, all P of X are Q of X. And the sentence, some P of X is Q of X. Now, I want to be able to write these sentences in terms of quantifiers, right? These aren't necessarily, don't think that the X necessarily has to be a number, don't be this way. Let me give you an example of something that you've seen in calculus. How many of you remember this from calculus? All differentiable functions are continuous functions, right? This is important mathematically, we need to be able to say this. Some continuous functions are differential functions, right? These are things that we need to express mathematically. So how do we express these in terms of quantifiers? This kind of thing that looks like an upside down A is for all, and it's backwards E. There exists. So, so one way to write the first statement, all P of X, Q of X. One way to write this is for all X, P of X is true, means Q of X is true. Okay, here's kind of a tricky one. How about the other one? How would we write that? Something. I'm tempted to write, there exists X, P of X. is positive X. Gotta be careful about that. There exists X, there's my sum X business. there exists an X such that P of X and Q of X are true. Now, it's tempting to say, that, right? I mean, I think we all agree that given what happened on the previous ones, it's tempting to think that might be the case. So I want you all to think about why this statement is reflected by this but not this. And I'll give you a hint when you think about this. Recall, if P of X is false, what is the status of the statement if P of X is false? It's true. So when you think about the difference between this and this, keep that. Okay, how'd you take that? Any questions? Well, let me know if you're having trouble with the homework, and I will see you all on Wednesday.